So thank you, Matthias and Elizabeth, for the invitation. And yeah, so I will talk about this joint work with Shay Sadovsky and Kasia Wyczesany, who are both present. And I will give a slide talk. So the first part will be more about the background. I will try to not spend too much time on it because usually I just get carried away and only talk about the background, because it's quite nice to see how everything works together, but I really want to get to actual theorems. So anyway, but the beginning is still background. So apologies to all of those of you who've heard me talk about this subject, because much of this you have already heard, the first, well, something like 10 slides. Right, so the premise is transportation of measures. So imagine we have some pile of sand, this is this X here, and some big hole, and we want to map all of the sand in X to this hole in Y. And the best way to think about it is actually to make both of these sand piles and just think about them as two measures, probability measures, let's say, so normalize them to have total measure 1, and we want to map the probability measure mu to the probability measure nu. So the somehow mature way to think about it, this Kantorovich way to think about it, is to think about transport plan, which is a probability measure on the product space, X times Y, which whose marginal in direction X is the measure mu, and marginal in direction Y is the measure nu. So this is written here. And this is maybe the picture. You put the product space, mu on one coordinate and nu on the other coordinate, and you look for measures gamma whose marginals are mu and nu. There are many such measures, which are called transport plans. So this is geometrically, you want the measure of this purple set above A to equal the gamma measure of the purple set to equal the mu measure of A, and the same for the nu measure of the set B to be the gamma measure of the light blue set here. And such measures or such pairings between mu and nu, they're called transport plans, and they're denoted by this capital pi of mu and nu. Okay, so this is the transport, these are transport plans. Now, there are also transport maps. That's a slightly stronger requirement. Well, not slightly, that's a stronger requirement when you want this transport plan to actually be concentrated on a graph. So you want some map T from X to Y, such that the mu measure of the inverse image of set B is the nu measure of B. So this just means that the measure gamma, as I said, is concentrated on a graph of a function from X to Y. And every transport map defines a plan, but not all plans come from maps. Okay, so these are transport plans. Let's put this on the side. The next thing you want to do is to talk about optimal transportation. So for this, you have to introduce some kind of cost function, which really measures for every pair how much it costs you to move a unit of whatever it is, sand, let's say, between the location X in X to the location Y in the space Y. You can think of X and Y to be Rn if you want. It's enough for this talk. This cost function which you introduced, it actually carries with it all of the geometric information of the problem you're talking about. So different costs really give completely different geometric things that are happening. And what you naturally want is to find a map or a plan which has small total cost, okay, or even maybe ones which minimize the cost. And if the cost can attain infinite values, then maybe a first thing would be to ask whether you can find such a plan with a finite cost even. So the total cost of a plan is what's written over here. So you integrate the cost with respect to this plan, okay? And the total cost between mu and nu is the infimum of such costs of plans for all plans which are transport plans between mu and nu. Okay, so this is a transport cost. Let's put it over here. Now, the basic theorem around this is Kantorovich's duality theorem, which tells you that there is a very beautiful way of writing the total cost between mu and nu. So instead of looking at the infimum of overall plans, you can instead look at a supremum. And what are you supremizing over? So you're integrating two functions, a function phi and a function psi. One of them is a function on X and the other one is a function on Y. And you take the supremal such sum of two integrals over pairs which satisfy this condition over here, that phi of X plus psi of Y is less than the total cost between X and Y. So Kantorovich duality theorem says that the supremum equals this infimum. And let's just notice that one direction of this inequality is immediate, because whenever you have a transport plan, gamma, then the fact that its marginal is mu on x and its marginal is nu on y means that this equality over here is true. So the integral of phi d mu equals the integral of phi d gamma x of y. So the integral over y gives you the measure mu, and the same for the integral of psi. And now, since this is a pair satisfying the inequality, then you always have, so this inequality over here comes from the condition of phi psi. Okay, so for any plan gamma, and for any phi and psi which satisfy this inequality, there is an inequality of the left-hand side is less than the right-hand side. And the point is, of course, when do you actually have equality? Can equality be satisfied? Okay, so this condition on phi and psi inspires you to define admissible pairs. These are exactly, so whenever you are given a cost, you can talk about admissible pairs with respect to this cost, forgetting about the original problem for a moment. So a pair is called admissible if it satisfies this inequality. Phi of x plus phi of y is less than c of xy. C admissible, so there is a cost around. And when you talk about admissible pairs, it also inspires you to define the biggest function, which is admissible together with phi. So this is the definition of the c-transform. So again, you're given a cost c, and then automatically you have a transform taking a function phi to its biggest admissible partner psi. Okay, so any psi admissible with phi has to be less than this infimum over here. So it has to be less than c of xy minus phi of x for any x. So it has to be less than the infimum, and this infimum is the largest admissible partner of the function phi. Okay, so notice that right away with the cost, you get a transform on functions, from functions on x to functions on y. I allow the functions to attain value plus minus infinity. You just have to be a little bit careful about summing plus and minus infinity. I'm not going to get into this right now. And this transform is very nice. So first of all, it's always order reversing. If you start with the bigger phi, you're going to end up with a smaller phi c. If you, just like I said, it's the biggest admissible partner. So for any other admissible partner of phi, phi c is more than that. And just using these two properties, it is quite easy to see that when you apply the transform twice, you always get something bigger than phi. And when you apply it 3 times, it's just like applying it 1 time. Okay, so this means that the c-transform actually is an involution on the image of the c-transform. So when I look at phi c, then I apply the c-transform twice, I get back to phi c. So it's an order reversing involution, but not on the whole space of functions, of course, but on the image of the c-transform. So this inspires you to define the c-class of functions. So again, you're given a cost c, you immediately get a class of functions, all of those which are images of the c-transform. Now they're functions on y. And on this class, the transform is an order reversing involution. Okay, automatically for every cost, you get a class of functions and an order reversing involution. Let me say right now that for this talk, I will assume that x equals y and that the function is symmetric. Otherwise, you have to distinguish between the c-transform on functions on x and the c-transform on functions on y. And I don't want to get, I don't want to have to distinguish each time, but really everything works the same also if x and y are different. But for this talk, c will be a symmetric functions on 2 variables, and the 2 variables will belong to the same space. I just call one of them x and the other y to, it's just easier to see things that way. Okay, please stop me at any point if there is any question. Okay, so back to this background slide. 4th thing we got from Kantorovich duality, we were inspired to define the c-transform, not just us, this is a well-known transform, and the c-class, which is the image of this transform. And these are exactly functions on which the c-transform is an involution, right? 2 examples just to see that this fits into convex geometry and things we always work with, at least in the asymptotic geometric analysis. The examples, usually my examples will have Rn as the base space. Quadratic cost, when you have quadratic cost, then the c-transform is just the Legendre transform, okay? But you have to write the Legendre transform on the appropriate function. So the function is not the function phi, but x squared over 2 minus phi. When you apply Legendre to x squared 2 minus phi, you get x squared 2 minus phi c. Okay, and this is a very easy computation. Okay, right, so Legendre is with the supremum and c-transform is with the infimum, but this is exactly this minus that comes in. This is very easy to check, right? And the second example is taking the polar cost. This is minus logarithm of x dot y minus 1. And when you plug the polar cost with these two spaces, then again, it's not hard to just compute that the C-transform is no other than the polarity transform A on functions, which was discussed in my works with Vitali Milman, and it was actually defined by Rockefeller in 75 book, but then it didn't receive much attention. And in like the past, I don't know, 10 years, we gave a lot of attention to this transform on functions. And yeah, this is maybe what inspired us. Well, this is what inspired us for this whole project, but for now, this is just one more example. Okay, polarity transform A of psi is the supremum of x dot y minus 1 over psi. This is a transform from convex form. Well, it's defined on any function, but you always get a convex function which is non-negative and vanishes at the origin. These functions are called geometric convex functions. Okay, and the C class is thus not geometric convex functions, but actually minus logarithms of geometric convex functions. This is the C class associated with this polar cost. And I should say that the fact that this transform comes from this cost was, I don't know if to say discovered is the right thing, but it was, we understood this in a master's project with my student Hila Barel, and also joined with Yanni Rubinstein, who is also part of the origins of this project. Okay, so we wanted to study polarity transform, and one step in understanding it is realizing that it really comes as a C-transform for this specific polar cost. Okay, so these were just two examples. Now, the fifth thing still in the background is what is a c-subgradient of a function. So let's go back to the proof I showed you for Kantorovich duality theorem, one of the directions, one inequality. The theorem is an equality, but one inequality I showed you that it holds trivially. And notice that if we want this inequality to actually be equality over here, okay, so this inequality here, if I want it to be equality for a given plan gamma and function phi, oh, maybe I should say before. So notice that I changed from looking at phi and psi to looking at phi and phi c, because it's the biggest admissible partner. So if I want to supremize, obviously I'm going to take the biggest possible admissible partner of phi. So I'm looking only at phi and phi c, and I can even do this again. I can look at phi cc and phi. Okay, so this is why I'm only looking at phi and phi c, and I'm actually assuming that phi is in the C class, because I will anyway want to take a function in the C class. So it's just going to make it bigger. Okay, so, oh, I don't know why this is each time. Okay, so if I want to have this as an equality, then I see immediately that what I need is I need phi of x plus phi c of y to equal c of x, y. But I don't need to be equal everywhere. I need it to be equal gamma everywhere, or gamma almost everywhere. Okay, so this is the next thing I wanted to say, is that for equality in this inequality, what we need is that gamma will be supported, or more specifically, more accurately concentrated. So gamma of the set where x and y, well, where phi of x plus phi c of y is c of x, y, has to be 1. This has to happen almost everywhere. Okay. So this inspires you. Now I'm using the word inspire too much, but I don't know, my English is disappearing somehow. So the c-subgradient associated with a certain cost and a C-class function phi is exactly this manifold of pairs x and y, which satisfy this as an equality. So here, just notice that here you always have an inequality no matter what x and y are by the definition of the C-transform, but I want this to be equality. This is the definition of the C-subgradient of a function. Okay. Now for Legendre transform, you remember the Legendre transform we mentioned before, then, oh, maybe I should say one word before. Oh, oops. So for this to be satisfied as an equality, this just means, remember the definition of phi c was infimum of c of xy minus phi of x. So this really means that this infimum is attained at x, exactly. So this is another way to think of the C-subgradient. These are all the pairs xy, such that when you compute phi c of y, then the infimum is attained at exactly this point x. Okay, so for Legendre transform, because of this modification, because this is just a modification of Legendre transform, it's just like asking where is the supremum attained? And it's very easy to check where the supremum of the Legendre transform is attained. It's not always attained, but it is, when it is attained, it's attained exactly when y is in the subgradient of phi at x. Okay, so this is why we call it the c-subgradient, because for the classical cost, this is really somehow a modification of the usual gradient or subgradient. Okay, so now we have almost all of our background. We know what transport plans are, transport cost, optimal cost. We have Kantorovich duality theorem. We define the Ctransform and the C-class associated with a given cost, and the c-subgradient associated with the cost. Okay, and what we're interested is in talking about optimal plans. Okay, and like I explained, the way to have an optimal plan one way to get an optimal plan would be to make sure that your plan is supported on some c-subgradient of a function. Whenever you are able to find such a plan, you are sure already that this plan is optimal. And when this is possible, then phi is called a potential for the plan. So finding potential is really a key step in understanding optimal transport plans with respect to a given cost. Okay, are there questions so far? Because this is the background or the first part of the background. Okay, very good. So now let's recall that for the classical cost, these kind of things are very well studied. Okay, the classical cost I call the quadratic cost and the usual subgradient instead of c-subgradient. This is well studied and also super, super useful. And this is the well-known Brenier map. So the theorem of Brenier and McCann is that whenever you have two probability measures on Rn, very, very general conditions. So let's assume that mu is absolutely continuous, although you don't have to, you can also relax this a little bit. Whenever this is the case, you can always find a convex function phi. So phi convex is exactly the C-class associated with the quadratic cost, such that the gradient of phi, so I even didn't write subgradient, but usual gradient, because it exists mu almost everywhere for a convex function. Okay, and transport plans, you just need to define them almost everywhere. So you can always find a convex function, and its gradient is actually a transport map of mu to nu. Okay, so there is a transport plan supported on the gradient of this function, and this already, like we said, implies it is also optimal with respect to quadratic cost. Of course, to use Brenier map, you don't really usually care that it's optimal, you just care that you can find such a map, but really what happens is this is the optimal map with respect to quadratic cost. Okay, so a leading question would be, what happens if we change the cost function? Of course, like I said, for us, what we wanted to change the gradient to the polar gradient. And for this, we had to change the cost to the polar cost. And then we started thinking about this question more seriously. Okay. So what happens? If the cost is a cost that always gets finite values and some other good properties that I'm not mentioning here, then most of the things for the Brenier-McCann theorem actually work very well. Okay. So what you have to do is you have to use some reasoning for why there exists an optimal plan. For this, you need this goodness on the cost or on the measures. Once you have an optimal plan, you use some general nonsense to show that the plan has to be supported on a cyclically monotone set. Actually, I have to write here C cyclically monotone because I'm talking about a general cost, but still finite valued. Okay, but what like Rockefeller theorem is for usual cyclically monotone. It's C cyclically monotone with respect to quadratic cost. And then when you know that your plan is supported on a C cyclically monotone set, then you use the Rockefeller-type theorem to show that this already implies the existence of a potential. So there is a very famous theorem of Rockefeller saying that cyclically monotone sets are precisely the sets that lie on the subgradient of some convex function. And there is an extension by Ruthendorf that says that the same is true when you exchange the quadratic cost with a general cost, so long as the cost attains only finite values. But like I told you, the polar cost, which was our main motivation, does not obtain finite values. So remember, it's logarithm of x dot y minus 1. So whenever x dot y is less than or equal to 1, this cost is infinite. So it's minus logarithm, sorry. Okay, so what is our main result? Our main result talks about cost functions, and this I should emphasize, which are allowed to obtain infinite values. Infinite values means that there are actually certain points x which cannot be mapped to certain points y. So there are obstacles within your transport problem, okay? And our main result says that whenever mu and u satisfy some condition, which I call strongly C-compatible, and I will explain it in a moment, okay? And whenever you have a cost, and this happens with respect to a cost, which is allowed to obtain infinite values, I do assume it is continuous. You can relax also this, but I do assume it is continuous. And some condition, which I don't want to elaborate on, which is some boundedness of the cost from below, So for instance, if your cost is positive, that's fine, but also if the measures are compactly supported, then any continuous cost will be bounded from below. But essentially bounded, it's not really an important condition. It says that there are two integrable functions such that their sum is below your cost. It's not an important point here, okay? So whenever you have two such measures and there exists some finite cost plan between them, so this is the second condition, assume that the total cost is finite, then you can always find an optimal transport map. Okay, but this was actually known. This follows from some theorems in Villani's book. But what's new is that you can not just find some optimal transport plan, but you can actually find a function phi, a C-class function phi, and the plan is concentrated on the c-subgradient of phi. So this is the new thing. This is a Brenier-type theorem for general costs, and we call the cost non-traditional if it is allowed to assume, or if it sometimes assumes the value plus infinity. Okay, this is the main theorem. Of course, for this theorem to be interesting for you, you have to understand what I mean by strongly C-compatible. So before I define strongly compatible, I'll define something which I call just compatible measures. And for this, just notice that for there even to exist some transport map which is finite cost. So for this cost to be finite, for the existence of any transport map with finite cost, there is a necessary condition which just says that any subset B you start with, so let's think now that we're transporting y to x, it doesn't matter, it's completely symmetric. Any subset B and y, you have to have enough points in x that you can transport to B, right? Because you have to transport into B at least, or exactly, the measure nu of B. So there have to be enough points in x that are allowed to be mapped to this set B, so that there is some y and B with finite cost between x and y. Okay, so this is a trivial necessary condition for the mere existence of a transport plan with finite cost between mu and nu. Okay, so this I call C-compatible. If this happens for any subset B of y. Okay, and actually maybe you can't see it in 1 second, but this is symmetric between us. So if I change here the roles of mu and nu, then this is the same condition. We can show that. And what do I call strongly C-compatible? It's exactly the same condition, but when with the inequality becomes sharp. Okay, so I want not only there to be enough points in x that can be mapped to B, but I need a little bit of space. I mean, there need to be a little bit more even points that can be mapped into B than this necessary condition applies. Okay, so this is called strongly C-compatible, and this condition has to hold whenever well, of course, if nu of B is 1, then I can't expect this to happen. So I should assume that nu of B is not 1. And also when the mu of this set over here is 0, it's also, I can't have a strong inequality. So this, I assume this only for sets which are not of measure, which are of non-trivial measure. So not everything and not nothing. Okay, so this is strongly C-compatible. And now the theorem up to saying what is essentially bounded from below, the theorem is is given. Okay. Oh, sorry, wait, sorry, this is the iPad, blah, blah, blah. And this is the definition, okay? Let me write a corollary from this theorem. What happens when you apply this to not just any cost, but this polar cost that I told you was our main motivation. So this is a corollary. Consider the polar cost on Rn, okay? Then given two measures on Rn, such that there is some finite cost plan between them. Assume this strongly C-compatible, and strongly C-compatible here means this funny-looking condition. So I look at a set and it's polar, it's usual polar, and I measure the mu measure of the set and nu measure of the polar. Actually, it's enough for K to just consider convex K. Okay, so of course it's enough. Then I need this sum to be less than 1. And again, less than or equal to 1 is a necessary condition. So if it's not, if it's sometimes more than 1, then I'm sure that there will be no transport finite cost map between them, plan between them. But if I have a strict inequality and also this essentially bounded from below, here it translates to some moment condition on the measure. So for instance, if they both have finite second moment, whenever this happens, you can always find an optimal transport plan with respect to the polar cost. And moreover, it has a potential. In this case, the potential means a C-class function, so minus logarithm of a geometric convex function. And this plan is concentrated on the c-subgradient of this function. And this is actually, well, I did not define polar gradient, but those of you who know our previous work, this is really the polar gradient of this geometric convex function. Okay, so this is the corollary of the theorem for the cost that we started, well, that was interesting for us in the first place. Okay. Okay, so let's talk about this theorem. This is the main object of this talk. Okay, so let's discuss first what goes wrong with the original proof, with the proofs for the traditional cost, with the Rockefeller or Ruthendorf type proofs. So first of all, the first issue, which is really a non-issue the way I stated the theorem, is that sometimes finite cost plans just don't exist. So sometimes there's obstacles are so big that you just cannot find a finite cost plan mapping one measure to the other. Okay, but here I assume that there is a finite cost plan. So this is not really a problem for us at the moment, but we'll get back to this. It will play a key role in what I'm talking about. The two other steps, the two next steps, one of them is showing that once you have a finite cost plan, there is an optimal plan using some compactness Polarity type theorems. And also the third step, saying that when you have an optimal plan, it has to be supported on a C-cyclically monotone set. These two steps work perfectly. Now, I should say I did not define yet what is C-cyclically monotone. Some of you know this from general knowledge, but I will talk about this in the next slide if you do not, okay? But this is some important geometric property that just holds somehow by, again, general nonsense for optimal plans with respect to a cost C. So these two steps actually work perfectly. But the main point is that the fourth step, which was to say that if a plan is supported on a C-cyclically monotone set, then it has to have a potential, this Rockefeller type theorem, it just fails. When you have a non-traditional cost with infinite value, you can find a counterexample, I will show it in the next slide, where there is no potential. Okay, so this will be our starting point. Okay, but for this I have to define what is C-cyclic monotonicity because I did not so far. Okay, so C-cyclic monotonicity, the intuition is the following. Assume that you're just trying to map these blue points to the red points. Okay, and you're looking at the discrete case, and you're looking at the optimal plan, at the optimal mapping between them. Okay, so if it's optimal, this means that if you're going to switch, if you mapped one blue point to a red point, and then you switched with a different pair, then you're only going to lose. Okay, because this is what it means to be optimal. Okay, and not only if you switch between two, but in any permutation you do to your plan, then it's just gonna cost you more. Okay, so more formally, I write it like this. So for any finite number of points, 1 up to xi, yi, I from 1 to m, if I take some permutation, so here sigma is some permutation on 1 up to m, okay, then if I change it, instead of mapping xi to yi, I map xi to y sigma of I for all i's, then it's going to cost me more. Okay, so this is a very natural condition for optimality, that this has to happen. And also for if the cost is continuous, then it's not just a pointwise condition, then optimality implies this for points, because small neighborhoods of them will have approximately the same cost. Okay, so this motivates the definition of C-cyclically monotone, which again, in the Rockefeller case for quadratic cost is a very well-known definition, just called cyclically monotone. And a set is called C-cyclically monotone if there is one condition here which you're probably not used to seeing, because usually costs are finite valued like with quadratic cost. But if the cost is not finite valued, then I first of all want all of the costs to be finite in my plan, in this G. Okay, so if all the costs are finite, and then also whenever I make a permutation, and here I just did a cyclical permutation because it doesn't matter, right? I can rename the x's, the indices any way I want, so this is completely general. So for a cyclic permutation, then the cost of the original matching, which is induced by G, is just smaller than the cost of the new mapping or matching. Okay, and I wrote this cyclically, so ym plus 1 is just y1. Okay, so this is called a C-cyclically monotone set, and you can forget everything else. I mean, this is just a definition of a property of a set, some geometric property of a set, but it's connected with the cost, right? So different costs induce different notions like this. Okay, an easy observation is that if you have a set G which is already in a c-subgradient of some function phi, then it's automatically c-cyclically monotone. Okay, let's see why. So by definition, being in the c-subgradient means that phi of xi plus phi of yi is c of xi yi. Okay, but for any pair for any pair, oh, I don't know what's happening with this guy. I can't move it. Okay, for any pair, you have an inequality, right? By the definition of phi c of the C-transform of phi c of yi plus 1 plus phi of xi is less than the total cost. And now I just sum. I sum over I, both of the equations, okay? And the sum on the left-hand side is the same, right? I'm just summing all of the phi on all of the xi's and phi c on all of my yi's. So you get an inequality between the sum of the costs, okay? So you get exactly the inequality that you wanted. Okay, so let me say this again. If a set is included in a c-subgradient, then it's automatically c-cyclically monotone, right? And Rockefeller theorem talks about to what extent is the converse true? So is it true that whenever I have a c-cyclically monotone set, for instance, if I got it by taking an optimal map, so I know it has to be monotone, then is it true that it's included, that it has a potential? It's included in some c-subgradient, okay? And Rockefeller theorem, Rockefeller-Ruschendorf for general costs, tells you that indeed this is true. So a set is c-cyclically monotone if and only if it has a potential. It's included in the c-subgradient of some C-class function, okay? And actually, so our paper also gives a new proof for this theorem, but there is also a beautiful theorem, a beautiful proof of Rockefeller and its extension by Ruschendorf by really just building this function. Okay, but you see here that I wrote in red the fact that the cost is real valued. Okay, and it really uses, the proof uses essentially the fact that the cost is real valued, and rightly so, because the theorem just fails if the cost is allowed to attain infinite values. Okay, so when a cost is allowed to, so we can find a cost which attains infinite values and a c-cyclical monotone set which just doesn't have a potential. And we call these costs non-traditional. This is also in the title of the talk. A cost is called non-traditional if it's allowed to assume infinite value, well, if it actually assumes infinite values. And the example is just a one-dimensional example. It's very simple. So it's this polar cost that we started by studying very seriously, which is why, we can find many examples just using this cost. So it's one-dimensional, so it's just minus log of x times y minus 1. It's a non-traditional cost. And here is a set, okay? This is a set in r times r, in x times y, which I claim is c-cyclically monotone and has no potential. Okay, so here I also wrote the formal definition of the set. Of course, it's really not important. The point is this hole that it has in the middle. Okay, so the set has to be in the finiteness set. So let me just draw this. So this is the finiteness set of the cost, x times y more than 1. Okay, so you're not allowed to have points on the boundary of the set because there the cost is infinite. Okay, and I claim two things here really, right? First of all, I claim that this set is c-cyclically monotone. And I also claim that it doesn't have a potential. The fact that it's c-cyclically monotone follows from the fact that it lies on the graph of a decreasing function. It's very easy to check that for this specific cost function, being c-cyclically monotone is equivalent to being monotonely decreasing, okay? And the fact that it doesn't have a potential really follows from this hole that you see in the middle, right? Because what does it mean to have a potential? It means that you have some function phi in the C-class, in this case, some geometric convex function or minus logarithm of a geometric convex function, such that phi of x plus phi c of y equals minus log x times y minus 1 for all x's, for all pairs xy on G, in G, okay? But this expression, this minus log x times y minus 1 goes to infinity as I approach the hole, okay? It goes to infinity, which means that one of these two guys has to go to infinity. But this hole is somehow in the middle of the domain of both phi and phi c. So the domain of phi is somehow x and the domain of phi c is here at y, but the hole is in the middle of both of the domains, so they can't go to infinity in the middle of the domain if they're a convex function or minus logarithm of convex function. So this is not the formal proof, but it's not hard to make it into one, and this set does not admit a potential. Okay, so Rockefeller-Ruschendorf theorem fails if the cost is non-traditional. So what do you do? What can you do? Well, what we did is we found a new property of a set, which we call Cpath boundedness, which is equivalent to lying on a admitting a potential, to lying on the graph of a c-subgradient of some C-class function. So let me explain the definition of this property of a set being Cpath bounded. Okay, so again, I have a set G in the product. of x times y. When will I say the Cpath bounded? Well, first of all, I want, again, the cost to be finite for every pair in this set. This is one condition. But the second condition looks a little bit different. So I want for every pair of points in my set G, so I call them x start, y start, and x finish, y finish, okay? Such 2 points, there has to be some bound, which only depends on these 2 points, okay? It doesn't have to be the same bound for all pairs of points, but it only depends on the starting and finish point. Such whenever I take some path between them, so whenever I plug in new points, xk, yk, and I call x start, y start the first point and x, f, y, f the last point, then when I check the total cost of the original sort of matching coming from G, and then I subtract the cost of switching and checking what is the cost of mapping xk to yk plus 1, then this difference has to be bounded, okay? Let's draw this. So I have my starting and finish point, and I want for any points in between, any number. So this is 5, but any number m of points in between. When I go between them, and each time what I measure is the cost of the original point minus the cost of the x of the original point and the y of the next point, this total sum has to be bounded, okay? Let's compare this with c-cyclically monotone that I defined just before. So c-cyclically monotone was very similar, okay? What it said is that this difference of the total cost and the total cost after changing an index has to be negative, okay? But here my starting and my ending point are the same. I'm actually doing a cycle, okay? Because ym plus 1 is actually y1. So it looks actually, in some sense, cyclically monotone looks stronger, right? Because I'm asking for a bound of 0 and not for a bound of just any number m. But it's very easy to see that if my set is not c-cyclically monotone, so if I can find some difference like this, which is positive, then I can go over, and the starting and the ending point are the same. So now I have a cycle that starts somehow starting from x1, y1, and ending back in x1, y1, okay, with some points in between, okay? Then if when I go around the cycle, I accumulate some mass, then I can go over the cycle once more, any number of times, and accumulate any positive, any as big as I want number. So it won't be bounded by any number m. In other words, what I just said now was that Cpath boundedness implies c-cyclic monotonicity, okay? By just taking the starting and finish point, the same point, okay? Now for real valued cost, it's actually equivalent. So c-cyclically monotone and Cpath bounded are equivalent. And this is also very easy to see because all I have to do is I have to do one, oh, let me clear, okay, I don't know how you clear everything, sorry. Really, I don't know. Okay, I'll just do it manually. Okay, because all you have to do is just do one more step like this, and then your starting point and your finish point are the same. Okay, so we really get a cycle. So you just have to add here one extra term, and you get that the sum is less than 0. And then you just move it to the other side, and this will be your bound m. Okay, so if the cost is finite, so if this final step always has finite cost, then you are fine. Then c-cyclically monotone implies Cpath boundedness. But the point is that when you look, when you look at these terms that you're adding over here, this guy is sometimes minus infinity. Now, when it's minus infinity, you're fine, right? Because you only want it to be less than or equal to m. But if you added a guy and then you know it's less than 0, and the guy you added was minus infinity, then maybe, maybe the total sum was not bounded, and it became less than 0 because you added to it something which is negative infinity. So Cpath boundedness does not follow. So this, this is not true in general for non-traditional costs, but it is true when the cost is real valued. Okay. Right. So now we have a new notion of Cpath boundedness, and the big point is that with this notion, we have an exact sort of analog to the Rockefeller-Ruschendorf type theorem. So Cpath boundedness, if and only if you have a potential. This is really the property that you need to have a potential for a given set, okay, for a set to live on the c-subgradient of a function. Okay, so this is in a paper that we recently uploaded to arXiv and submitted, and this is one first result, and the proof is very nice. I'm not going to talk about it. Using Zorn's lemma is actually quite, let's say, naive approach, or quite easy to read, I think. And it also gives a new proof of the Rockefeller-Ruschendorf theorem, which is somehow by elementary inequality kind of thing. Okay, going back to our main result. So we said that Rockefeller theorem failed for non-traditional costs, but now we replace it with a Rockefeller type theorem, where instead of C-cyclic monotonicity, you have to exchange it to Cpath boundedness. Okay, so the fourth step somehow changes, but then you have to look back at the third step, right? Because the third step said that general nonsense promises you that an optimal plan is supported on a cyclically monotone set, not that it's supported on a Cpath bounded set. Okay, and this really can fail. So sometimes your optimal plan will not have a potential. This actually sometimes happens. So now we have to understand what properties on the pair of measures imply that actually the optimal plan is supported on a Cpath bounded set. Okay, and this is the strongly C-compatible. This is this property that I said here that we have to discuss a little bit more. Okay, and to discuss, okay, if you say so. So we have to discuss it a little bit more. To discuss it, let me go back one more time to the Cpath boundedness versus C-cyclic monotonicity. So again, Cpath boundedness tells you that you have to find a bound like this, which holds for any somehow m-1 points between your starting and your finishing point. Okay, and this was the picture. Now what you can do is you can form a graph, just like I drew over here, and you connect up 2 points, x, y, and zw, which are in your set G, if the cost of x, y, and the cost of zw are finite, because you're in a set G, which is in the finiteness zone. But you're gonna have an arrow in your graph if the cost between x and w, so between the x of the first point and the y of the second point, is finite. This way you form a graph, okay? And if this graph is connected, and this is a directed graph, so I say strongly connected, any point has a directed path to any other point. If you show this, then indeed, what I told you in the previous slide says that C-cyclic monotonicity is equivalent to Cpath boundedness, because, you know, going back from XF to XFYF to XSYS, you can do it in many steps. You don't have to do it in one step. Okay, so long as you have one path connecting between them, then you can do what I said before about looking at this sum over here and adding to it all of the terms in this new path, saying that the total thing is less than 0 by cyclic monotonicity, and then taking this guy and moving it to the other side. This will be your M. This will be your bound. Okay, so you can always do this so long as you can add these arrows, which all have not cost, which is finite, not negative infinity. Okay, because this guy, like I said before, it can be sometimes infinite, in which case when you know, because it's with a minus sign, you actually added a minus infinity to your sum, and it's, you know, it's not a big deal that it's now negative, that it's less than or equal to 0. You can't move it to the other side. Okay, so this is something we'll get back to. That strong connectivity of this graph that I just defined is what helps you get from C-cyclic monotonicity back to Cpath boundedness. Okay, we'll get back to this. But okay, this was our plan, like I said. And now before talking about this, what I really have to discuss with you is the existence at all of finite cost plans, because this will actually, this is very much connected to what I just said about connectivity. You can't see it right now, but you'll see it in a moment. Okay, so we get back to this problem one more time and address the first issue, the issue of even existence of a finite cost plan. When can I be sure it even exists? And this has to do with this compatibility of measure, which I defined to you when I told you about the theorem, but we didn't really discuss it. So now let's discuss compatibility or C-compatibility of measures, okay? So back to square one. We have a cost function. We are given two measures. Let's assume they are discrete because that's easiest to think about. When does there exist a finite cost plan between them? And in the discrete case, when everything is discrete, this is just Hall's marriage theorem. So I think you all know it very well. So I have a bipartite graph. One side are the points in X and the other side are the points in Y, okay? And I'll put an arrow if C of XY is finite. These are my arrows. Okay, so I have my points in X, my points in Y, and the arrow just tells me that I can map this point X to the point Y without paying an infinite number of dollars. Okay, some finite number. I don't care what number, because everything here now is finite in this picture. And what I want is I want a matching in this graph, right? A finite cost map is matching between the red and the blue. And Hall-Marriage theorem tells you that the condition is that for every subset of the X's, if I look at the subset of Y's which have some arrow from this subset pointing to it, so this is kind of my subset B, and I look at all the points Y and Y, such that there exists some X and B with an arrow, so CXY finite. So if for every subset B, the number of points in Y is more than the cardinality of B, then I can find a matching, right? And in this case, this happens, and this is my matching, okay? So this is Hall's marriage theorem. This is for the finite case. Let's put it here just to remember, okay? And for continuous measures, a necessary condition, like I told you before, is exactly this. So if I have two probability measures, for the mere existence of a transport plan with finite costs, or even more, for the mere existence of a transport plan supported on the set of finite cost, a necessary condition is that there are enough points in X that are allowed to be mapped to B, and this has to be for any subset B. And like I said, this is a symmetric condition. So equivalently, I can say that for any subset of X, there are enough points in Y that can be mapped to this subset A, enough in the sense of measures, okay? So this is a necessary condition, and this is called, we call this C-compatible measures. If this happens, if this doesn't happen, then you're sure that you're not going to find a transport map with finite costs between them. You're absolutely sure, okay? Geometrically, let's put this geometrically. So I called S this finiteness set, all the pairs with finite cost, and here is a picture, okay? So this strange looking, I don't know, octopus is the set where the cost is finite. And I want for every subset A of mu, I'm looking at, so this is my subset A, I'm looking at all the points that can be mapped to this A, okay? So this is the set, right, with finite cost that can be mapped to A. So this is the set of points that have some option of A being mapped to them. All other points, if I'm going to map a point on A to some point outside here, it will have infinite cost, okay? Right, so this is the condition somehow geometrically. And strong C, oh, wait, let me go back just, sorry. Go back a little bit more, okay? So, and here I have an inequality, weak inequality, okay? But when can there be equality here? For equality here, what I need is I need my gamma measure, this transport plan, to have nothing outside, so no measure over here, right? Because the total gamma measure of this set is all of the measure, you know, on this whole big strip, right? So for equality here, what I need is I need all of the measure of gamma on this strip to be supported on this set that I'm coloring pink, and nothing to be outside. So I know there's nothing outside in the white places because they're of infinite cost, but I need also nothing outside in the part of the octopus which is within this slab, okay? And usually this doesn't happen. If this happens, it actually says that your transport problem, I'm not going to talk about this, but your transport problem can be decomposed into two different transport problems. So you know that all of A is mapped to this point and everything outside of A is mapped outside of this set, sorry, not point, outside of this set, then you have a decomposition. So when this doesn't happen, then we say that the two measures are strongly compatible. Okay, so you have a strict inequality between the measure of the set to which the points can be mapped and the measure of the original set. Okay, so long as the measures are non-trivial. So this is this condition of strong C compatibility. Okay, and I left here this condition for you to see, but let's discuss also for one more minute the case which I called half discrete, and this is when I have two measures and one of them is discrete, because this is also, you can sort of partially understand this geometrically, or you can understand this geometrically. So now assume that you have a measure mu. Okay, let's think about it absolutely continuous, but your measure nu is actually a discrete measure. So you're mapping a whole set of, a whole somehow absolutely continuous measure to some discrete set of points yi. So y now is just the set yi, I equals 1 up to n. Okay, and there are some weights on these yi's, and this is your measure nu, a discrete measure. Okay, So what is strong C compatibility? Looking down here, it says that for any subset of y's, okay, but a subset of y's is just a subset of 1 up to m, okay, so for any subset of 1 up to m, which is non-trivial, so which has measure, which is not 0 or 1, I need the sum of these weights, I need the total measure of these yi's to be strictly less than the measure of the set which has finite cost with one of these points, the union of all of the sets of finiteness with each of these yi's, I and j. Okay, now this is a polytope, right? Because alpha I, so I know that sum of alpha I is 1, right? It's probability measure. And these are more conditions on these alphas, okay? It's part of the simplex, of the m-dimensional simplex, okay? And alpha has to be in the interior of some polytope. We call this the Hall polytope. And if you were in Shay's lecture in this AGA seminar of Galina, then you heard a lot about this, okay? So this defines a polytope. And a strict inequality means you're in the interior of this Hall polytope. And in this half discrete case, this was maybe that's what the first time we really understood what was going on. We were able to show that for alpha in the interior of this polytope, you can really map the measure mu using you can really find a potential mapping the measure mu to this measure nu with this weight vector alpha. And this we did using a method which this very beautiful paper of Keith Ball, where he gives a new proof for the Brenier-McCann theorem using Brouwer fixed point theorem. So it really shows that there is a certain mapping with potentials that takes the measure mu, to any point within the interior of this polytope. So in Keith Ball's proof, because the cost was classical, the polytope was really the simplex. So it was a little bit easier. Here you really had to work quite hard to show that you can find for any point in this polytope, in this Hall polytope of alphas, you can, you can always, I'm sorry, what happened? Sorry. You can always find a potential mapping it there. Okay, so this, I call this the half discrete case when one measure is continuous and the other discrete. Now, the problem we had here is that we weren't able, so in Keith Ball's proof, what he did is he said this for discrete measures, and then he took some limiting arguments. So it went there, it goes quite smoothly, then you can somehow approximate any measure nu with this discrete measures and everything works perfectly. Here, that didn't work. We weren't able to make it work, so we had to think of a different proof for general measures mu, and this actually gave a very, a very nice different proof for the whole thing. But this was part of the way we got there. This also tells you why it makes sense to look at a strong inequality, because for polytopes, it just means the interior of a polytope. And in the last part of this lecture, I want to talk to you about really, so this C compatibility, how we use it and what's the geometric meaning of it. And this also hides some very nice, you will see now, so if you lost me, this is a good time to come back, a very nice duality theory for sets, new kind of dualities for sets. Okay, so I repeated here the definition of strong C compatibility. So for any set, I wrote it here for in the dual setting. So the measure of A for any A is less than the new measure of all the points that are allowed to be mapped to A. But I can rewrite it like this. So instead of writing nu of the points that there exists some x in A with finite cost, I'm writing that it's 1 minus the measure of the complement. So y is such that for all points of A, they're not allowed to be mapped to them. Okay. And I can also move this to the other side. So this is this condition mu of A and mu of the set associated with A, all of the points that have infinite cost, no matter what point in A I take, the sum of these measures has to be less than 1. And this inspires you once more to define a kind of dual of a set. Okay, so I'm given a set A, and I'm given a cost function, and I'm taking all of the points Y such that their cost with all of the points of A is more than some fixed number T. Okay, and T can be infinity. So what strong C compatibility is using T equals infinity, but let me write this even more generally. So any T can be in R or infinity, but you fix it. Okay, you fix this T. So this is a weird definition, right? But it has some nice properties, just as is. Just look at this definition, forget everything else. So when I apply this duality twice, I'm writing just dual, but this dual with respect to a cost C and a number T. When I write it twice, then these are points that have cost more than t for all points in A dual. And of course, all of the points of A have cost more than t for points in A dual. So this includes the original set A. And when I apply it 3 times, it's just like applying it once. So this is very reminiscent of the C-transform, right? It has the same kind of properties, but now it's a transform on sets. Okay, so given a cost C, you get a kind of duality transform on sets, subsets of the space, let's say Rn, okay, which on its image is an order reversing involution once more. Okay, now for polar cost and t equals infinity, this is just usual polarity. Okay, because infinite costs means x dot y less than or equal to 1, and this is polarity. Okay, but for other costs, this is a totally different order reversing transformation on sets. And it's quite exciting to see what it gives for different costs and different t's. I won't give such examples. This is part of work in progress together with Kasia and Shay, so we're studying these as well. But if you remember, so those of you who were in Vitali's talk, so the reciprocal body is a kind of dual of a body with respect to a different cost, not the polar cost, but some variant of it. And many other transformations on sets can be obtained this way. Even taking just a quadratic cost is kind of exciting, right? Because what is the dual with respect to quadratic cost and some t? This is the complement of the t neighborhood of the set. Okay, so I give it a set, and now I look at the complement of its t neighborhood. And when I take the complement of the t neighborhood of this guy, then I get something which is bigger than my original set. It includes my original set. Sometimes it's bigger, and on some class of sets, it's actually equal. And this is okay. Anyway, I have some more things to say in the 2 minutes I have left. Okay, so now I can write this condition in a more elegant way. So this condition really says that mu of A and mu of this dual with respect to cost C and t equals infinity of A has to be less than 1. This is strong t compatibility. And one more way to write this is if already I have in my hand some transport plan, then instead of mu of A, I can write gamma of A times Y. And instead of mu of A dual, I can write gamma of X times A dual. And this sum has to be less than 1, right? So in this picture, I see that the sum of the measure of the purple set and the measure of the blue set has to be less than 1, okay? But this in particular means that there is some measure outside, right? Because the sum of these two measures, well, there is some set that I'm counting twice, but anyway, even when counting it twice, I have total measure less than 1. So there is at least some density point of gamma outside. And this is really what we are using for the connectivity of that graph. Okay, so what we are using is that for any transport plan, the measure, the gamma measure of whatever is left outside here is positive. So there is some density point there. And this is really what we needed to use to get the connectivity of the graph. I only have 1 more minute, so I don't think I'm gonna, I did leave some proof because I like to have some proof in the talk, but we really just have 1 minute and maybe you are tired from seeing a proof. So let me just press the thing. So this is the proof how you use this to get connectivity of the graph that I mentioned before, this graph connecting 2 points if the cost of mapping the x of one point and the y of the other point is finite. And you can use this thing, I'm not going through this, but it's really nice that this duality thing for sets really enters very directly into there. And when you use it and separate into cases, you can show that actually the set G, or well, the set G doesn't have to be connected, but it has to have a subset of measure 1, which the graph of which is a connected graph. And then you get that C. Oh, okay, let me say the last thing. And then you get that Cpath boundedness really is implied by a C-cyclic monotonicity once you have connected this. And this really completes the proof of this theorem, which I called our main result. Okay, so I think I'm just on time. I know this was very quick, but I really wanted to get a chance to talk about all these results and not just give a lot of background, which I like to give. But anyway, I think this is it for now. Thank you for your attention. I hope you enjoyed.